nucleophilic substitution. Let's have a think about another mechanism. Specifically useful when talking about, or used, sorry, when talking about halogens. You need to know the definition of a nucleophile. The definition of a nucleophile is an electron pair donor. You can work out what a nucleophile is if you aren't confident on the definition, because nucleo, the nucleus of an atom, is positively charged. Phile means likes. So a nucleophile is a species that likes positive charge, is attracted to a positive charge. So an electron, a nucleophile, sorry, is going to be attracted to an area of positive charge and able to donate a pair of electrons to that positive charge, or willing to donate a pair of electrons to that positive charge. So a nucleophile is an electron pair donor. It's kind of my thought process in it. Nucleophiles can attack a partial positive charge or a fully positive charge, actually, if needs be, resulting in substitution occurring. Let's think about an example mechanism. We've kind of already thought about it, or we've at least thought about the beginning of it, but let's just make it simple as possible. Okay, so one of the things that I try and do, and we haven't got a huge amount of time, so I can't spend ages doing it, but if we had all the time in the world, then we would. But one of the things I try and encourage students to do when thinking about mechanisms, rather than just learning the mechanisms rote and just recalling them exactly as you have learnt them, trying to understand them. If you can understand them, then if you're given an application of knowledge question in your exam, you're not stumped. If you can understand how species interact in a mechanism, then you can apply that theory to any new situation. If all you've done is memorized how you get from A plus B to C and D or whatever, then if you're not given A and B, then we might have a minor panic attack in the exam. So I would 100% recommend you think about how are these species going to interact. Here we have got halogenoalkane. So what's interesting about that halogenoalkane? The interesting thing that's going on is that the halogen is much more electronegative than the carbon. That creates a polar bond. That polar bond is attractive, or the positively charged carbon, sorry, the delta positive carbon, I should say, is attractive to a nucleophile. And I'm going to call my nucleophile NuC, and I'm going to give it a full positive charge. Not all nucleophiles do have a, full negative charge. Not all nucleophiles do have a full negative charge, because ammonia, NH3, can act as a nucleophile, and it doesn't have a full negative charge. But in this case, just for simplicity, I'm going to use an example with a nucleophile that has a full negative charge, like hydroxide, for example. That lone pair of electrons, how is that going to interact, that negatively charged nucleophile, or that lone pair of electrons, how's that going to interact with my halogenoalkane? Well, electrons are negative. They are attracted to positive things. They are repelled by negative things. That's just our basics of attraction and repulsion with positives and negatives. So these electrons are going to be attracted to, oops, why is that not drawing? Let's try again. Oh, I've got a funny dot now, never mind. Oh no, why is this not working? I wonder if my pen battery's run out. I'm just going to give it a second to see if it can recharge, but it has just been recharging. It shouldn't be... It shouldn't have run out because it was charging all through lunch. There we go. Maybe it was just having a funny five. Okay, there we go. We're back, sorry. So the lone pair on the nucleophile is going to be attracted to that partial positive charge. That's where that's the direction in which the electrons are going to move. They're going to move towards the thing they're attracted to. That carbon can't have 5 bonds. It's got a pair of electrons that are being attracted to it, so it would form 5 bonds if something else didn't happen. So in this case, that pair of electrons in the bond is going to move away and towards our halogen. That means we end up with our species, which has now got the nucleophile on instead. And in this case, it's X minus. Let's just double check we have done a balanced equation. We have got an overall, we've got the same number of atoms on each side of the equation. So it's tick, we've got conservation of mass, and we've got an overall negative charge on the left-hand side of the equation and an overall negative charge on the right-hand side of the equation. So I haven't lost or gained any random electrons. Yay, I've got conservation of charge as well. Oops, I might have slightly written on my next bit, never mind. So that is an example of nucleophilic substitution, specifically SN2. If you are an example that covers SN1 and SN2, we're not going to look at it specifically today because it isn't all exam boards. But have a think about how you know it's SN2 and what SN1 would look like if it was different and why. So reactivity of a halogenoalkane here is determined by, as always, a dominant factor, but there are contributing things or there are conflicting things. So dominant factor. There are two things that can contribute. The strength of the carbon-halogen bond can contribute to how reactive a halogenoalkane is, and the polarity of the carbon-halogen bond. The more polar a bond is, the more reactive it's likely to be, usually. That's why halogenoalkanes are more reactive than alkanes, for example, because alkanes don't have polar bonds, halogenoalkanes do. But also the strength of the carbon-halogen bond is going to play an impact. It's going to have an impact as well. The stronger a carbon-halogen bond is, the more energy is required to break, and therefore the less reactive it is. Let's just pop that down. So stronger carbon-halogen bond requires more energy, which is going to make the halogenoalkane less reactive. And polarity of the carbon-halogen bond, more, the greater, the greater the, let's just jump straight to it. The greater the polarity, no, that doesn't make sense. The greater the dipole, that's better. The greater the dipole, so the bigger the electronegativity difference, and therefore the greater the dipole, for the nucleophile to attack, the more reactive it's going to be. So we have got two conflicting factors. What is the dominant factor then? The dominant factor is the strength of the carbon-halogen bond. Both play a part, the same as we were talking about with our trends in periodic table, they both play a part, but the dominant factor is the strength of the carbon-halogen bond. So we'll link this to hydrolysis in a second because that comes up in your specifications. But both are interesting to talk about and think about, but the dominating factor, or the thing that determines how reactive a halogenoalkane is the strength of the carbon-halogen bond. So